Good. So today let's try to finish first the identification of dynamic systems. There is one more, at least one more dynamic model, which I would like to show you and maybe say why it might be interesting for you. And then we will switch to, as we did for the linear regression, we then talked about some practical aspects. How do I choose a order of the model? How do I choose some inputs to the model? So let's do it also for the dynamic systems. So last time we have dwelled into this world of dynamic systems identification. And I hope, well, also during your exercises, you get fond of the models like finite impulse response. It's trying to somehow approximate a transfer function. It is relatively nice in several cases. One of the principle is that it will only try to learn from the inputs, or only try to predict from the inputs what will be the output. Might be interesting in some applications, and yet the more interesting type of model, or something which you are more used to from your theory of automatic control and so on, is the ARX model, which can very easily represent linear transfer functions in the discrete time domain. It's basically the same thing, it's just different label. And what we were talking about is how to fit these coefficients if we are given some data. So I guess you went through all the nice matrices that we discussed at the lecture, also during your exercises. One more interesting model is an extension of the ARX model, and it is so-called Armax model. So it will be like a combination of ARX and something which is called MA, and this MA is just moving average. So the whole name would be what? Auto-regressive moving average model with exogenous input. Yeah. In a similar fashion as our, just to remind, autoregressive model with exogenous input was formulated. What was our formulation? At the end of the day, its prediction equation looked like this. So now we are adding some moving average. What kind of moving average? So it's a prediction equation. Prediction equation would look something like this. We will keep our past outputs, that's why the auto-regressive. So we have again this term AI times some past inputs. I goes from where? From 1 to not mn. Then we will add the new term, which will be a moving average C times some E. I will tell you in a second what this E means, and we will keep our exogenous input. Okay, minus I for I goes from 1 to m. Yeah, so if I just cover this part, this will be our good old ARX model, transfer function. What is this new part? So yeah, it is some error, exactly. So the auto-regressive part is this one. The exogenous input is the part with the U, and the last but not least, the moving average is this guy here. How does this error look like? This error is trying to repair the model. The error is basically taking the output that we really measured online in some past. Yeah, remember this ek to the minus I means that we are only looking at the past data. So it's trying to see whether there is some discrepancy what we predicted in the past and what we observed after that. So this is no longer a type of model where you take historical data, 1 year of the data, you train it, and you just let it run and predict. This one is trying to correct itself while it is running. It's correcting it. Basically, it's trying to do some moving average of the previous errors. Why do you think this model could be helpful, or why would you what kind of application it would have? Not an easy question, so don't worry if you haven't heard about this.
For example, if we are looking like a system of 2 days, we can somehow say that as we, for example, figure all the way details, so we can leave that way that there won't be any spillage from it, or like the height of, for example, so we can somehow predict it.
Yeah, one situation. Okay, leakage of a valve. So basically, what you described is well, usually when we do identification, basically on the historical data, we just collect the the pairs of instances of the inputs and outputs, but well, we never thought about having some disturbances in the picture. So, for example, a leaking valve would be a good example of a disturbance, and this disturbance can, of course, happen in the historical data. So actually, when training the ARX or FIR models, we are completely neglecting the fact that there is some disturbance. If the disturbance is measured, yeah, somebody puts the sensor to the temperature of the ambient to something which you might think of a disturbance. Of course, this disturbance can become an input of the model. And when doing the prediction, you might either use some weather forecast to predict the ambient temperature, stuff like that. If the disturbances are not measured, nobody will tell you that suddenly we are operating the reactor at the different conditions because we have a different quality of the feed to the reactor. It's quite hard to detect, but well, this model will actually try to detect this and learn some coefficients. Learn some coefficient C that will basically keep the information about the possible disturbances that happened in the history in the past at the plant. So it's in some form you are freeing your coefficients A1 and B1, so the ARX part, from absorbing all the errors that are presented in the disturbances. You are basically saying, okay, the coefficients A and B, you are learning the true dynamics of the plant, and this part, coefficient C, are responsible for taking into account the errors, let's say the systematic errors in the data. It might not be very easy to train. Basically, we need the nonlinear optimization for it in many cases, and you might now ask the questions: how do you predict? Because, well, this is a prediction equation, but if we wanna predict into the past, into the future, we don't have these measurements in the future. So what would be usually assumed that this EK would follow again some normal distribution, zero mean, and some variance. That is, well, I'm not gonna say it's the best thing you can do. It's one of the things you can do to assume this. So at least you can assume, okay, in the mean case there is no disturbance. You can create some sort of scenarios what can go wrong in 1 sigma, 2 sigma, 3 sigma cases of the disturbance striking the system. Clear? Somehow? Okay. If we are clear on this, so let's go to the main thing we wanna discuss today. Let's see how much we can manage. Let's discuss some practical aspects of system identification. Yeah. Of system identification. Basically, it starts with what are all the necessary steps? What is the algorithm if I'm seeing some black box? If I'm given some task. Well, there is a device, and we wanna find out its mathematical representation or the mathematical representation of its behavior. So what? Imagine the situation. You get our nice Flexi device for the first time, and you wanna get to the you wanna get some mathematical representation, some model of the behavior. What are the steps?
Try to change the one variable and find out how it affects the others.
Change
Find
one.
some correlation between them.
Okay. Okay. So basically, what you are trying to do is to say, I'm gonna design an experiment. Oops. All right. I need to find what inputs I'm providing. Yeah. So maybe even before this, wouldn't you actually read the manual for the for the device? I guess, right? Or make ChatGPT to read the manual. But okay. Or you will ask somebody, yeah, if you will come to the, I don't know, refinery or some other production plant. You will try to get some prior knowledge. How does it work? What can I expect? Is it fast? Is it slow? So this is something which either you can get in some documentation, in some manual, or simply talking to people. There are tons of undocumented things and features in every plant. So you'll try to get some prior knowledge, and based on that you can basically find out what kind of experiment I'm going to try. Find out, let's say, UK. So when designing an experiment, what do you need to think about? How long will the experiment run? If I know from prior knowledge how many inputs are there, how many inputs I should change, when should I change them? And this design of experiments is a whole study field, which we are not going to study deep, but basically there is there is a difference in supplying inputs to your plant, let's say in this classical form as some step, or maybe doing something more advanced. Let's say I do just the short short step, then I do a longer step, then I do a shorter step, and I get back. What would you feel is would be the difference?
Between these two?
Mm-hmm.
You don't have to necessarily reach steady state when we do this short step.
Mm-hmm. And what will be the outcome if you supply? So let's think about some dynamic plant, and well, maybe the good example, because how is it at this point you have actually no idea whether the dynamic model of the plant is first order, second order, third order, whether there are zeros and any stuff like that. So basically, if we have let's say we have one slow and one fast pole. So what we will measure in the case of a step response, well, this is too nice. I should maybe say it looks like this, where maybe you are used to see some nice smooth curve, and then decide like, okay, if this goes rapidly up, then this is the first order system, and if there is some sort of a delay, this will be a second order system. It might not be even visible, and this is still a very nice noise, very nice picture, maybe after some filtering. But so you can get to the steady state, and basically you can get some dominant time constant, but it might not be obvious. It might not be easy that you actually get the fast pole. It might be completely hidden. So what would happen in the case of the second input? So the first one is like medium change. What's going to happen? The first part should be the same as the step response, but then we will get back with our input to the zero. So it's like start of the second step response. The other one, maybe we already get lucky, and we get to the step response. And what would this short, almost like impulse type of input tell us? Well, if there is some slow pole, the input would not even, the output would not even react to it, right? Because it doesn't have this enough time to see the rise time of the response. If there is a fast pole present, then there will be at least something. Doesn't have to be like completely visual to your eye. It has to be visual to the mathematics, to the let's say some standard deviation, some deviation from the mean. Only slow pole. So it might be quite beneficial to use this form of the signals, and this form of a signal is is usually called PRBS. Many nice abbreviations here, and it's called pseudo random. Hyphen is not necessary. Pseudo random binary sequence. And you should actually test it in your exercise. Well, pseudo-random binary sequence. Why is it binary? Jumps between 1 and 0. Of course, it can be manipulated to jump from 0 to 10 or whatever. It's usually designed, or you will usually, if you generate some random numbers between 0 and 1, you will get this shape of the input. Good. So I designed the experiment. I collected the data. What now? What should I do? Process the data. Okay. What is the outcome? What do I need from the processing of the data? What do I need to find out? What I want to find out?
Well, our quest is to model this.
Mm-hmm.
So we need to do the things we did this semester to make the data better. So, for example, standardization.
Okay. Mm-hmm. Mm-hmm. Okay. So this form of processing. Okay. Mm-hmm. Makes sense. Good. So collection and pre-processing. Pre-processing of data. Mm-hmm. So it's about well, okay, standardization, seeing what are the magnitudes of the data. Mm-hmm. What then? What would you do if you
Then we can, for example, create like the data set.
Mm-hmm.
Is already processed somehow.
Mm-hmm.
So, for example, the outliers are out.
Mm-hmm. Okay.
And we could do nonlinear regression and try to look if our data fits some model we know, for example, first order linear model or second order linear model.
Mm-hmm.
And look for which regression is the best.
Why is it nonlinear regression that you do?
Maybe it could be linear if I said that we. Yeah,
I mean,
we are looking for linear.
yeah, you are kind of starting with the harder thing. So my recommendation is always start simple. But Exactly. We are going. Well, we want to fit the model, so we need we need the data we have. Now we need the model. So what form of the model? We can even choose like several forms of the model and compare them. Yeah, we had this training, validation, and testing data. So let's maybe call it choose model set. What do we need to decide? What is the quality of the model? What are the features of the characteristics of the model? That's already too specific. That gain is specific to dynamic and linear model. Yeah, so these were already.
Parameters of the model?
In what sense I decide them?
If we choose a model set, it's like the data or the type of regression, let's say.
Type of regression.
Because, for example, you can, for example, Flexi was described with like multiple, with one equation, and there were multiple like parts of it. One was logarithmic, another was inverse, another was, I believe, linear. So I believe like you can choose the right model and then you can look for the parameters.
Okay, but yeah, looking for the parameters is a next task. But you mentioned it. Well, we need to decide whether the model is linear or non-linear, right? We might.
Or we can somehow linearize it. It's also possible.
How do you? Well, you are choosing them. Basically, if you are choosing a linear model at this step, you are basically linearizing. You are just saying I'm going to learn a linear representation of this data. So you would.
I thought that if we do the same step change in different values output, and to see if the gain is constant or
Exactly.
the time constant is constant.
Yeah, exactly. This is what I wanted to ask, like how you would actually choose this. Where are my pictures coming? Okay, pictures are here. Yep. Either we. No. I wanted to. So let's say this is our first step change, this is our second step change, and this is our third. Okay, let's maybe make it somehow equal. Something like this, Jakub, like doing the step change in a data, I don't know, let's say to the value of 1, 2, 1, 2, and 3, or 1/3, 2/3. Because what can we say then, and what you have probably seen in your experiments with Flexi. So what would you say about this picture? how would you think about it? How would you assess it?
I would say that it's non-linear.
Because of.
Because if it's linear, the change, for example, in the input, is like the same height of the block, and the output isn't proportional to it.
Yeah, exactly. Yeah, that would be so. Equation like this, which is just a steady state. Well, this is a static gain, which is like just a steady state equation for the dynamic system. Well, cannot basically get this one. And what if you maybe one more teasing note? What if you see output like this? So not this guy here. What if you see this?
There's minus in front of it. There's minus in front of it.
Where?
Well, it's very non-linear.
Right. It can happen that the system is so nonlinear that the gain can change its size, its sign, while in the first case that we just have unproportional scaling of how the inputs in the how the outputs in the steady state react to inputs. That case can be nicely solved with integral control action. Well, stuff like that. This one is much harder. It's basically impossible to control it with a linear controller. So even the LQR, none of the easy stuff would work. So that's a red alert if you see this behavior. This one is non-linear but bearable. Yeah. Okay. But what does this say? Well, suddenly we wanna here decide about choosing a model set, but that this means that we already should have these inputs planned in our original experiment, right? So there are many times there are feedback loops in this process. So it's not like always a linear algorithm. Of course, well, another example. This is maybe silly, but what if we see this type of a response? So we do the step change, and basically we just see the scaled step change in our data.
I would say that this is discrete system.
So the change is immediate.
Or it can be discrete systems and with a large sampling period, for example. So when this is
Well, it's okay. Now I understand what you mean. Yeah, it's discrete system all the time. Yeah, continuous systems are good in theory, but well, once we are, of course, all the systems are continuous, but we are getting discontinuous data or discrete data.
There is no need for dynamic system.
Exactly, for dynamic model. Why to bother? Yeah. There is no information about the pole, zero, whatsoever. So I mean, of course, you can say I do my Rmax modeling, I train all the parameters, and this MATLAB, Python, Excel, or whatever will give you some numbers. Why wouldn't it? but these numbers won't actually represent anything. You will very soon find it either in the validation data or even worse in the testing data or in the testing at the plant. So yes, we should decide whether the model is static or dynamic. Okay. What else should we decide? Yeah, maybe some other stuff, like we will get to this, like the order of the model. Let's call it model order. Maybe something like, is there input delay? Would we consider input delay in our fitting procedure?
Maybe when we were talking about linear and nonlinear, we could do like the step change from 0 to 1 and then backwards, and to see if the time constant is the same. Maybe it will go faster.
Okay. Yeah, some sort of a hysteresis, stuff like that can also happen. Yeah. Another interesting situation. Right. I mean, this is critical thinking. All of these things, can somehow go wrong. If we are dealing with a stable system, we are we are in a very good charted territory. Yeah. For the unstable, what can we actually do? What do you think?
We can try to stabilize it.
How?
With the controller, for example.
Mm-hmm. Oh.
Like with inverted pendulum, for example. It's an unstable system and we can stabilize it.
Exactly. Yeah. So if unstable, then basically what we need to do, design a stabilizing controller. This is, of course, a chicken and egg problem, because, well, now you say, if I want to design a stabilizing controller, I need to know the model. But if I need to know the model, I need a stabilizing controller. Yeah, but okay, there are ways. Well, at least some sort of a trial and error. If you are in the situation that this plant is running for some years in some production facility, it might be the case that there already exists a stabilizing controller. Basically, what does this situation mean? That we have our plant and we cannot longer design an experiment in our control variable, but we need to have the control variable designed or supplied in the way. Supplied in the way that our output is stable. Controller. Yeah, the standard picture. What can we then do to design an experiment, to run an experiment?
Put it all in one box.
What does it mean? Put it on. Okay, put it on in one box. Good. What is the input?
Model overview with controller and blend inside.
Yes. And how do we? Well, okay. So let's say the plant is in steady state. The controller is in steady state, and that's your data. That's you know the situation basically like this first part. You cannot really learn anything about the time constant, about the delay, about poles, zeros. So how to get some data for dynamic identification, or let's just test whether the system it's dynamic. Seeing the dynamic in this picture.
We do step changes with references, and if we know the exact mathematical model of controller, we can
Exactly, right. If we let's say if our time constant, well, time constant t would be negative, so our pole is positive, we can get the closed loop.
We still have the unstable plant.
Well, we now add some controller. I don't wanna derive it, and I also do not remember it. Don't you remember by any case how would if we just use the P controller, if the controller is just some KR, how would the closed loop?
The denominator was the characteristic equation.
Yes. Okay. Well, I wanted already the, yeah, good. So we have KRK. I was already thinking about, you know, like the expanded form. So what do we have here? 1 plus K TS plus 1, something like this. How would it look like? We need the common denominator to get rid of TS plus 1. You have done this right in Theory of Automatic Control 1. So what do we have? We have... am I doing this correctly? TS plus 1 plus KRK. Something like this? Or am I missing something?
The first one, we saw the first one more.
What's the first one more?
The one was GC, the first, yes.
Yeah, controller?
Yeah, we had GC and GS.
Yeah. Could work. Yeah. So well, basically, okay. We need to just design KR. Well, the whole question is whether by choosing the correct KR we can push this unstable pole to be stable, but should work probably, right? Yeah, if this K is positive, probably we need a negative K. Yeah. The whole thing is, the whole point is that, well, this again can be fitted as a ARX model. Yeah, you can transform it to the discrete time and work out what the coefficients of this model are. just to recall, this is now I wrote R here. Yeah, this is now the relation between the response and the reference value. And still our unknowns. There are 2 unknown parameters that can be translated to some ARX model. Make sense? Okay. Any other funny example that comes to my mind? I mean, there are a few more, but not that significant. So maybe let's try to get an. So how can this work as an algorithm, or some kind of a flow chart? We start with some data collection, prior knowledge. Just trying to see how to plot this. So we can design an experiment. Let's try it like this. Experiment design. We can use some prior knowledge for that. Okay. Once we design an experiment, we do what? We collect and pre-process the data. So we have let's call it data collection. Once we collect the data, we should decide about the model structure. How did we call it here? Choose model set. Where we will again use the prior knowledge. So now we have yeah, we already covered all these. Now we have the data collected and pre-processed. We chose the model set. What we can do even further, we can choose. I think Jakub has already mentioned that choose some fitting criterion. Let's say whether we are okay with the least squares or not. What does it basically mean if we assume or we see in our data that we are dealing with some Gaussian noise, normal distribution of the noise, then we might just choose the least square fitting. Least squares. Good. And now if we have these ingredients, well, we can finally calculate the fit or fit the model. Right. We need all these 3 ingredients. We need to know what model we are fitting to, what data we are fitting, and what do we deem to be a good model. What then? We have our model fitted. so let's say test the model. Oh no, wait. Test the model. Let's shift it a bit. We will need one feedback arrow. Okay, so if then what?
After the test, we can say if the model is good enough.
Mm-hmm.
And also we can, for example, say that there are some limitations. If we use inverted model, for example, like 1 divided by x, for example, where x is the fitting parameter, then we cannot use 0, for example.
Mm-hmm. Ah, okay.
Like
So.
or we can see that, like the curve is it's copying the curve almost perfectly. For example, we can better use for input like 200 and 300. So we can say that we can use the model only for this part of data.
Okay. So basically, in the good and developed societies, it should be always like the model is coming with some sort of a certificate. Yeah, it was trained in this domain. It uses this kind of mathematical expressions. So use it with caution all the time, and don't use it outside of this domain. Yeah. And well, if our answer to whether this model is okay is no, well, basically then we introduce this feedback loop, so we can either go to the very beginning and design a new experiment. Well, maybe we have found out, okay, our model is our plant is unstable. We fitted a stable model to it because we choose wrong experiment, wrong model set. So we can also get back here, and also we can get back to the fitting criterion. Maybe if there are too many outliers which we cannot somehow discard, maybe we have good reasons for that, we can select fitting criteria like sum of absolute values that helps a bit with the outliers. Yep. Okay, maybe the last interesting thing, or the next interesting thing, it's not the last, but is how to choose the model order, especially in the dynamic systems. How did we go about this? How did we select what inputs, what independent variables will our model use if we had the static case for the linear regression, let's say?
So only gain.
Okay.
Maybe I didn't understand.
When we wanted to decide, should our model contain, I don't know, pressure plus temperature? Should our contain only pressure? Should our model only contain temperature? How do we choose this? The regressors, for example. Okay. Okay. So correlation analysis. Good. The question would be, well, what we have a similar task here. Basically, well, how do our models in the dynamic world, how do the dynamic models look like? Well, basically there will be some terms which represent the past data. So the task is actually relatively similar here. Well, we just need to select what past values would our model include. Let's say the first and second sample to the past, and not the third one. Which one should be omitted? And correlation analysis can really help here, but it's not as easy as it was in the case of a static systems. Well, in the static systems, basically we try to find some, how did the correlation look like? Well, we took the let's say values of the pressure multiplied with the values of the outputs observed. Usually subtracted the mean from them, yeah, because they should be at least centered. Well, and we made a sum of the sum of them, and well, yeah, if this data were additionally normalized, this would be something like our correlation coefficient between pressure and the output. Now, well, we are heading to something quite similar, but we now have to somehow do which movie was that? Somehow Inception, and also somehow Interstellar. Let's see, maybe Inception. What we want to do? We wanna compare. We have some signal y, and we wanna see whether the value of this signal that it takes at the time k is somehow correlated to the previous point, and we want to repeat this. We want to do this for the entire time series. Yeah. So, well, the easy approach is just we take a copy of this signal. We shift it. No, we shift it backwards. No, yes, backwards in time, and caps k minus 1. Sorry, I'm just discoordinated my plotting. And basically now, well, here we have the copy of the signal at time k, so it's just shifted. Well, and now we can actually do basically the very same thing as we were doing with our pressure and whatever the output was. Well, we can do the correlation coefficient of the signal in itself. So this is why the name comes, and this name is autocorrelation. And we will even find autocorrelation function in MATLAB, Python. I guess maybe also in Excel exists, wherever we can process some data. So there are several abbreviations here today. So the autocorrelation function. Let me just get the correct expression. Where do I have some autocorrelation function? Yeah, basically some mean. Yeah, mean is what I was missing here, right? Mean, and now we are summing. I goes from 1 to n. No. Do we need? No, I will. I will come here. ik minus I. So what's going on here? Basically, we can now decide what we have done in this picture. Okay. What we have done in this picture, we just found out how to do the correlation, autocorrelation. If we shift the signal, the yellow signal will just move back one sample. So basically, we got our original signal Y, and our yellow signal here was just shifted by one sample. But we don't have to stop there, right? We can also shift the second signal 2 samples. So that would tell us whether our current value at the time k is correlated with the value 2 samples ago, and basically we get the so-called autocorrelation function. I'll show you some examples in a second. Move. Good. No. Okay, don't move. How it looks like, but just before that, there is one more function that will come to our help, and that is called partial autocorrelation. Autocorrelation function, PACF, that's standard abbreviation. It will be almost the same as the autocorrelation function. So if you are thinking about autocorrelation function, just think about correlation coefficient. So how much is the signal related to itself if I shift it by several steps backwards. And the partial autocorrelation functions, it will gradually, if there is a correlation with the within the delay of the signal, within the unit delay of a signal. So let's say if I take the black signal, copy it, shift it backwards in time to get the yellow signal. So if there is a correlation in black and yellow, Then the partial autocorrelation function, when calculating the correlation coefficient for the red signal, would remove this correlation from between the black and yellow. It's very crude explanation. Let's see how it works in the examples. So our first example here is it sort of. Why cannot I move these guys? Ah, now I can move them. Nah, okay. Let's see. Many examples, but maybe hopefully they are illustrative. First example. We are just having this is going to be, this is a plot from MATLAB. You can also get it. We just take Gaussian noise. Yeah, so these are just samples from the random noise. You can see the mean is probably around 0. The standard deviation probably around 1. The equation, the behavior of this signal is like what? Each new value is not dependent on the previous value, right? We are just, it's like rolling a dice. Any new attempt, any new sample does not depend on the previous one. So that's why, if we calculate our sample autocorrelation function, so how does this plot work? Here on the horizontal axis, we have something, it's called traditionally lag, which we would maybe intuitively call delay, but this is really the values. Oops, I cannot write on it. So this is really values of the eye. Yeah, what is plotted there is this function. For 0, it will be basically a correlation of the function with of the signal with itself. For value ACF at 1, it will be a correlation with this signal shifted. So what we can see, what is the behavior that we observe. At 0, we basically get this. This is this stem plot that's by default in MATLAB. Well, we basically see that the signal has 100% correlation with itself, or that the signal either has a unit standard deviation or was normalized to the unit standard deviation, and this function will always do it. It will standardize the data. So what we can expect to see at the time 0 is the correlation with itself is to have the value of 1. What comes after? There is this blue band, and this blue band, it will try to internally calculate the statistics. What is the standard deviation of the noise, and it will create here, I guess it's a plus minus 3 sigma interval. So do not get distracted by any stems which are taking place, which are lying in this band. What does this plot basically say? We didn't indicate any correlation if we shift the signal backwards in one sample back into the past, 2 samples back into the past, and so on. In this case, the sample autocorrelation just looks the same. We will get to the plot where it will start to matter. Okay, and now I shuffled these too much by moving them, so I have to find out which one is the next I want to show you. Yes, this is the one. Right? Yes. Yup. So now it will get more interesting. Now we will have input and output. So the input in many examples will be just the Gaussian noise that we already saw, but the output will be given by some equation. You already recognize here this is the Fear model of the second order, and basically it's the moving average, right? Moving average. Basically, even if you look at the values which we are getting, yeah, so we start somewhere about 0. Then we have the our input is 1.5. So something about 0, 1.5 average is somewhere here. Okay, what happens here? The autocorrelation function, if we don't shift the signal by to the path of the correlation of the signal itself is again 1. This will be always 1. It will be normed there. We have only one significant value characteristics shown here. So basically it says if I shift the signal by one delay back in time to the past, the signal will be correlated with itself to certain degree. So what is this telling us? Well, basically it is suggesting us the fact. Can I write on this? Yeah, it's suggesting us this fact that yk is a function of uk minus 1. Maybe let's write a short note on this. Right, if we have, let's say our y1 will be 1/2 u1 plus 1/2 u0, y2 1/2 u2 plus 1/2 u1. So the correlation between u1 and u2, well, where is the correlation? What do they have in common? The u1, right? So, and even this 1/2 come in here. It's a suggestion of the 1/2 of the value of the output from the past will become 1/2 of the value in the future. Good. So, well, in this case, this is the data suggesting us that we should at least think about some dynamic model that is shifted at least one sample backwards. Again, there is nothing. Well, our our partial autocorrelation function again starts in a similar fashion, but then it deviates. It basically tries to just make a reason out of this noise, but it's not very successful in this for this signal. Maybe it would need a bit more data, not just 100 samples. I wouldn't bother. Basically, all these stems are getting close through this to this plus minus 3 sigma band of the noise. Let's get, yeah. let's get to this example. So now we change our model. Our input is still the same, but our model is now ARX model first order. This would be the behavior of the output. Okay. So let's have a look at our autocorrelation function. Our autocorrelation function, well, what should it get? It should sense that it actually might make sense to shift the shift the signal one time step to the past, or basically choose the model of order at least one. Yeah. So this is a dynamic model that we have in the hand. But the problem comes here. If you are looking at this plot and you take into account, well, okay, whatever is in this blue band, I disregard. I don't take care. But still, there are few stems which are more significant than the noise. So you might be even tempted to say, okay, well, this is a 10th order model, or maybe 5th order model. Yeah, this really comes here. It's sort of like an alchemy. You need to decide based on some experience how much you trust the data, how much you trust your previous pre-processing steps. Why is this happening here? Well, it's again, how would this prediction equation look like? So the output at time 1 will be 9/10 of output at time 0 of the initial condition, 1/10 of the initial input, and the output at the second time step will be 9/10 of y1 plus, well, something. We don't care about the u, because, well, we can rewrite this expression. We can basically plug in y1 from the first line to this y1. So we will find out what we have. 81/100 y0 plus and so on. So this type of a model, so the ARX, the type of the transfer function sort of models, will always give or show us some correlation, basically for several time steps. Yeah, because we can wind back, we can find out that even after the 10 time steps, our output was influenced by the initial condition. So that's why the autocorrelation function won't be as good in selecting the order as the partial autocorrelation function. So partial autocorrelation functions, I'm not gonna give you the mathematics now, but it will remove the if there was already identified correlation between the consecutive time steps, consecutive shifts of the signals, it will remove this from the picture. So that's why the partial autocorrelation function will basically suggest us this is just the first order dynamic system. So this was some sort of a signal. some sort of a signal. Let's see what's going to happen. This is wrong here. I forgot to change it. So now the input has changed. The system stayed the same. It's again first order, stable first order system, but our inputs are now, well, it's not the pseudo-random binary sequence. It's just jumping 0, 1, 0, 1, 0, 1, 0, 1. This is how the output looks like. Can easily simulate it. The picture is changed slightly, right? I mean, it's the same system. Just the input changed, yeah. So inputs matter, right? So we would expect to see something nice like here. Well, problem what helps in this case is exactly points like this where our inputs stay really well. They are not jumping too far from each other in the consecutive time steps. This one is just jumping up and down, so it can confuse. This correlation analysis. Just slightly, yeah. It's not the end of the day. What we are getting here, well, we just basically get the shift in this. It's just the sign of the correlation coefficient. That's not the end of the day. At least we can, after seeing the autocorrelation function, at least we can say, yeah, there is some dynamic behavior. There is some correlation of the past and present values. The partial autocorrelation, maybe it is slightly distracted. It would suggest us already a second order of the dynamics. I wouldn't bother here, because if the partial autocorrelation didn't signify anything significant after this long stem, I would just disregard it. The only possibility would be if we have some really seasonality, if something would be happening in like monthly cycles, stuff like that. But that's already quite advanced. Let's maybe briefly see nice behavior. Again, Gaussian noise input, PRBS should be even better, and we have some second order dynamics. The autocorrelation function has basically the same behavior. We see a lot of correlations with the output itself, but the partial autocorrelation is clearly suggesting us that we should at least take two past values, so select the second order dynamics. Okay, but it doesn't change with the coefficients. Do I have some more? There was one more, but now I cannot find it. Okay, doesn't matter. It's much better if you are having fun at the exercises with this. It's a helpful tool if you decide to go with the correlation analysis type of course. You will be even wiser, and you will use not only correlation analysis, you will also use cross-validation. You will create some training data, validation data, testing data to be sure that the model order you are selecting is the correct one. Make sense? Any questions? Was it too fast or too much, I don't know, pictures which you don't know what they mean? Okay, try it at your exercise.